In this lecture, we're going to discuss the three types of rocks and also what we can learn from rocks. So obviously, in a geology class, we're going to talk about rocks. And why do geologists care about rocks? Well, it's because rocks contain in them Earth's story. By learning how, where, and why a rock formed, we gather information about what was happening on Earth in the geologic past. So by learning rock stories, we learn Earth's story. Rocks act like a history book. If we can learn how to read the rock, we can learn how to read Earth's history. So first of all, what are rocks made of? Well, rocks are made of minerals, which are naturally occurring inorganic crystalline substances. They have a very specific chemical composition and characteristic properties. So for example, well, we have pictures of the mineral halite on the right, that's your normal sodium chloride, and it's what we call rock salt commonly. Another example mineral on the left here is quartz. That's SiO2, another very common mineral, silicon and oxygen. So that's what rocks are made up of. They're made up of minerals. And minerals are crystalline because the atoms that compose minerals are systematically arranged. So for example, this is a salt crystal. It's made up of, as we saw before, sodium chloride. And the sodium atoms and the chlorine atoms, they alternate in all three directions, which creates this cubic shape. And that's why salt crystals are cubic in shape, because of the way that the atoms in the crystalline structure align themselves. So that's why minerals are crystals. So rocks are made up of mineral crystals. Now, there are three types of rocks. There are igneous rocks, sedimentary rocks, and metamorphic rocks. And we're going to talk about each of these, starting with igneous rocks. So igneous rocks are rocks that form from the direct cooling and solidification of molten rock. So if you have liquid rock, molten rock, that cools and hardens, the resulting rock is an igneous rock. And there are two basic types of igneous rock based upon their texture. Intrusive, which are also sometimes known as plutonic igneous rocks. And then there's extrusive, which are also sometimes known as volcanic igneous rock. So intrusive and extrusive. Intrusive igneous rock, sometimes known as plutonic. Extrusive, sometimes known as volcanic. So extrusive rocks, ones, as I said, sometimes referred to as volcanic, they form from the rapid cooling of molten rock at or near the surface. So extrusive igneous rocks form whenever molten rock cools very quickly. As a result, tiny mineral crystals form, because it takes time for large mineral crystals to form, and because the molten rock cools very quickly, there's only time for very small mineral crystals to form. So extrusive or volcanic igneous rocks have very, very tiny mineral crystals, which gives them this fine texture where it has very, very small and indistinguishable mineral grains or mineral crystals. It's hard to distinguish one mineral crystal from another. Often it's impossible with the naked eye. So anytime we find extrusive igneous rocks, it tells us that there was molten rock at the surface or near the surface. So it tells us that there was volcanism, because volcanism is molten rock coming to the surface. So extrusive igneous rocks tell us that there was volcanism at this location in the past, or at least whenever that rock formed. Okay, I'll go back. A very common example of an extrusive igneous rock is basalt. Basalt is dark in color. It's actually what the sea floor, the oceanic crust, is made mostly out of basalt. An intrusive, or as I said, sometimes known as plutonic igneous rock, is one that forms from the very slow cooling and crystallization of molten rock deep beneath the surface. Because this molten rock is deeper beneath the surface, as it cools more slowly. And because it cools more slowly, there's time for large mineral crystals to develop. So intrusive igneous rocks develop this coarse texture where it has large distinguishable mineral crystals. So you can see the mineral crystals in this rock. If you look, you can see, light and dark mineral crystals. So intrusive igneous rocks mean that there is molten rock trapped deep beneath the surface where it's slowly cooled. And the most common example of an intrusive igneous rock is granite. Okay, granite is the most common rock found in continental crust. Okay, so basalt, an extrusive igneous rock, makes up most of the oceanic crust, and granite, an intrusive igneous rock, makes up most of the continental crust. So cooling and crystallization is what happens to form igneous rocks. Molten rock cools and crystallizes. It's extrusive if the cooling is rapid and it results in very fine or tiny mineral crystals. And so it produces an extrusive igneous rock. An intrusive igneous rocks form from the slow cooling of molten rock deep beneath the surface, which results in large coarse mineral crystals. That's an intrusive igneous rock. So as I said, basalt is the most common, one of the most common extrusive igneous rocks. Because it's extrusive, it has fine mineral grains, as you can see in this image. It's hard to distinguish one mineral crystal from another. It's because it cooled quickly above Earth's surface or just beneath it. So here's a lava flow, and this dark rock that formed from the lava solidifying is basalt. It's an extrusive igneous rock because it formed from the rapid cooling of molten rock out near the surface. Now, basalt isn't the only extrusive igneous rock. It's just the most common ones. Or granite is the most common intrusive igneous rock because it's intrusive. It has these coarse mineral grains that resulted from the slow cooling of the molten rock, slow cooling and crystallization of molten rock deep beneath the surface. And so here you see this red material is molten rock, and molten rock that cools down here and here will form intrusive igneous rocks because it cools slowly. Or molten rock that makes it up to here and comes out as lava, it will cool to form extrusive igneous rock. Okay. So where the molten rock cools determines, if, near the surface or deep beneath the surface, determines how fast it cools. And how fast it cools determines what size of mineral crystals it has. And that determines whether it's extrusive or intrusive. So here is andesite. Looking at a hand sample of the rock andesite, you can see that there are, some mineral crystals that look large in there. But if you look up close, you can see these little tiny specks in there. Those little tiny mineral crystals are the mineral crystals that make up these large splotches that just look like they're just one uniform material. So those in there, those really, really tiny mineral crystals, as we can see, that are almost indistinguishable with the naked eye. So for those tiny mineral crystals to form, the magma must have cooled, or the lava. So let me clarify. Molten rock beneath the surface is known as magma. If molten rock comes to the surface, once it's above the surface, that molten rock is now known as lava. So lava is molten rock above the surface, magma is molten rock beneath the surface. So because this has very tiny mineral crystals, it suggests that the molten rock cooled very quickly. And so lava likely erupts to the surface and cools quickly. That's likely how this rock formed. Move on to the next type of rock, which are sedimentary rocks. Now, sedimentary rocks form from the consolidation of sediment. And so what is sediment? Well, sediment is unconsolidated particles of material that are either created by the weathering or erosion of rock, or they're chemical precipitations from solution in water. So in other words, they can come from minerals that are dissolved in water, crystallizing out, or they can come from the secretions or remains of organisms. So that could also be sediment. So sediment can be particles of pre-existing rock, like sand or mud. It can be minerals dissolved in water, like the ocean, right? The ocean's salty. Why? Because there's minerals dissolved in the water. That's considered sediment. Or it could be the remains or secretions of organisms. For example, the shells of organisms or plant remains. So these three types of sediments, they're transported by water, wind, and glaciers. That's how they get moved across Earth's surface. And these three types of sediment, whenever they're turned into sedimentary rock, they form three different types of sedimentary rock: clastic, biochemical, and chemical. So clastic, well, first we'll start off with clastic sedimentary rocks. So clastic sedimentary rocks are sometimes referred to as detrital sedimentary rocks. It's another term for them, but I use the term clastic. And their clastic sedimentary rocks are those that are composed of particles of pre-existing rock. So it's made up of bits of other rocks. And so they get their name from the Greek word klastos, which means pieced or fragmented. So clastic sedimentary rocks are those that are made up of pieces or fragments of other rock. So how do we get from sediment to rock? Well, if you have a bunch of sediment, say like sand or mud, it just does not turn into rock. It just doesn't eventually turn to rock. Something has to happen to it to turn it into rock. And that something is the process known as lithification. So lith, if you remember, means rock. And so to be lithified means to be turned to rock or turned to stone. Similar to the word petrified, where petra also means rock. Petrified means turned to stone. So lithification is the process by which unconsolidated sediment, so loose sediment, is transformed into consolidated or solid sedimentary rock. And there's two steps in this process of lithification. First is compaction. The sediments have to be compacted. And how we compact the sediments, how the sediments are compacted, is that they're buried. They're buried under other sediments. So sediments are usually deposited by water. They can be deposited in other environments too, but often they're deposited by water. And what happens is more and more sediment is deposited at the same location. So sediments get buried by younger sediments that are deposited on top of them. And so as more sediment is deposited, the deeper sediment gets compacted by the weight of the overlying sediment. And that compaction reduces the space in between the individual grains of sediment, so they're closer together. The next step that's required is cementation. Cementation is whenever those grains of sediment that are not compacted are basically glued or cemented together. And this happens by water that seeps in between the grains of sediment. And inside that water is dissolved minerals. Now, in those dissolved minerals, they crystallize out of the water, which another word for solids crystallizing out of liquid or water is called precipitation. So those minerals, they precipitate or crystallize out of the water, and they form mineral crystals. These mineral crystals, they grow on the grains of sediment, and they interlock with each other. And so these mineral crystals are, as they crystallize out of the water and grow, they cement the grains of sediment together. So, common cements, common minerals that act as cement are calcite, which we'll talk about more. Silica, that's what quartz is made up of, silicon and oxygen, and iron oxide, or hematite, or it's rust, basically. Those are the most common cements, or minerals that act as cements. So here we can visually see that process. On the left, we see sediments are deposited. These are the grains of sediment and this is, the blue is empty space between the grains of sediment. The sediment is compacted by additional sediments being deposited, which reduces the space between them. Then as compaction, the final step is cementation, where minerals, in this case it's quartz crystals, precipitate out of the water, and those crystals grow together, interlocking the grains of sediment, cementing it together, going from an unconsolidated sediment to loose sediment to consolidated sedimentary rock. That's the process of lithification. So what are some examples of clastic sedimentary rocks? Sandstone is a very common example. So sand is obviously made up of sand, and it's clastic because it's sand is bits and pieces of rock. So because sandstone is made up of sand, which is bits and pieces of rock, sandstone is a clastic sedimentary rock. Shale is also clastic because it's made up of mud, which mud is really tiny particles of rock. So whenever that mud lithifies and forms a rock, it forms shale, which is another example of a clastic sedimentary rock. Okay, so the next type of sedimentary rock are biochemical sedimentary rocks. Sometimes they're also referred to as biogenic. Sedimentary rocks. And they form from the lithification of the secretions or remains of organisms. So that's where the bio part of their name comes from, because it has something to do with biology or life, right? So either the secretions of organisms or the remains of organisms themselves are lithified or turned into stone, forming a biochemical sedimentary rock. And some examples of biochemical sedimentary rock. Well, fossiliferous limestone. So fossiliferous means fossil bearing. So this is limestone with fossils. And so limestone is made up of calcium carbonate, which is the material that clam shells, oyster shells, mussel shells, coral, they're all made out of calcium carbonate. So whenever those hard structures, shells and exoskeletons of these organisms are deposited on the sea floor, they get lithified, compacted, and cemented together. They form what's called limestone. And because limestone is made up of the excretions of organisms, their shells and exoskeletons, it's known as a biochemical sedimentary rock. And so this one, you can see a fossil in it, the imprint of the inside of a shell, of a bivalve. So that is fossiliferous limestone. So the third type of sedimentary rock are chemical sedimentary rocks. Chemical sedimentary rocks form whenever dissolved minerals directly precipitate out of solution or water. So you have minerals dissolved in water that crystallize directly out of the water. So whenever this happens, the solids that are left behind are known as chemical sedimentary rocks. And so, for example, if you had a body of salt water that evaporated, all the salt doesn't go with the water as it evaporates, it's left behind. And those salts will crystallize out, forming chemical sedimentary rocks. As you can see here, is a body of salt water. As it's evaporating, the dissolved minerals are left behind in the form of chemical sedimentary rocks. So chemical sedimentary rocks are often referred to as evaporites because they usually form from the evaporation of water. Okay, so sedimentary rock environments are any environment in which sediment is deposited. So these are the environments that sedimentary rock form. And there's many different types of sedimentary environments, and we'll actually talk more about these in our next lecture, where we go more into depth with sedimentary rocks and their environments. But you'll see a common theme for sedimentary rocks is that they involve water, not all of them, but a lot of them, because water, as I'll learn, it transports and deposits a lot of sediment, especially running water. So the third and final type of rock are metamorphic rocks. Now, metamorphic rocks have this term metamorph in their name. You might have heard of the term metamorphosis, which, for example, a caterpillar goes through to turn into a butterfly, or a tadpole into a frog. And so it's a change, right? And so metamorphic rocks are rocks that have been changed or altered from some pre-existing rock that's been changed or altered. And this change or alteration is the result of a large amount of heat or pressure that the rock is exposed to. So whenever a rock is exposed to large amounts of heat and or pressure, the rock undergoes a change, therefore undergoes a metamorphism, and it's turned into a metamorphic rock. And there's two types of metamorphic rocks based upon their texture. The texture is the way a rock looks and feels. So it has large mineral crystals, it has small mineral crystals, and so forth. That's its texture. And the two textures of metamorphic rocks are foliated and non-foliated. So foliated metamorphic rocks, they possess a non-random crystalline or mineral arrangement. So non-random means that there's some order to them. Okay, so this non-random orientation, or this orderly orientation, so that basically the mineral crystals are aligned, that's produced whenever the rock is exposed to large amounts of pressure. So foliation results in the rock is squeezed. When the rock is squeezed, all of the mineral crystals, they align themselves and form a foliated metamorphic rock. So for example, you can see the pressure is acting in this direction. As a result, all the mineral crystals align themselves parallel to each other, perpendicular to the direction it's being squeezed. And so this rock will develop a foliation, this alignment of mineral crystals. Right? And so this is how a foliated metamorphic rock forms. It's from the rock that undergoes a lot of pressure as it's squeezed. For non-foliated metamorphic rocks, they do not possess a non-random crystalline mineral arrangement. So their crystal arrangement is still random. So their crystals are randomly arranged or oriented like most other rocks, like igneous and sedimentary rocks. And so non-foliated metamorphic rocks, they form whenever a rock is subject to large amounts of heat alone. It cannot be squeezed. Right? If it was squeezed, it was subjected to a large amount of pressure, would have developed a foliation. All right, that alignment of the mineral crystals. But because it's non-foliated, the mineral crystals are randomly oriented. That means it must have been exposed to heat alone. And so what happens whenever a rock is exposed to heat is that small mineral crystals, they recrystallize into larger, coarser, interlocking mineral crystals. And so here's an example of a non-foliated metamorphic rock. It's marble, it has these large, coarse mineral crystals. This is actually calcite. That's the mineral it is. This is a marble often forms on limestone. Remember limestone, it was a biochemical sedimentary rock, never made up of shells and exoskeletons. Whenever it's subjected to large amounts of heat, that calcite recrystallizes into large, coarse mineral crystals, forming the non-foliated metamorphic rock, in this case known as marble. So here we have a piece of sandstone. it's subjected to heat alone, right? It undergoes a metamorphism, and it forms a non-foliated metamorphic rock. In this case, it's known as quartzite. Quartz sandstone is exposed to heat and it forms quartzite. Now here's a piece of granite. It's exposed to not only heat and pressure. So what happens is it develops a foliation. So it becomes a foliated metamorphic rock where you can see the minerals are banded. That's this texture is called a gneissic texture. So this rock is a gneiss. The minerals have banded to these bands. So that non-random orientation we see here is what we call foliation. And the foliation always develops perpendicular to the direction the rock is squeezed. So because the foliation is in this direction, it tells us the rock was squeezed in that direction. So where are rocks exposed to large amounts of heat and pressure? Well, often at where two tectonic plates, which we haven't talked about yet, but we will talk about, where they converge, where they collide at what's called a plate boundary. So we'll learn that's where most metamorphic rocks form. They can also form in situations like meteorite impacts. Right, there's a large amount of heat and pressure, meteorite impact, which forms metamorphic rocks. We'll talk about metamorphic rocks and plate tectonics later. So when we talk about rock, okay, rock in the earth, you got to be careful what we're talking about. It's because there's, sediment and then there's bedrock. So most of the time, whenever you're looking at a piece of rock, you can hold it in your hand or something, or in your lab kit, you have these little tiny pieces of rock. Those are called hand samples, right? And that is technically sediment. Even if it's a large boulder, like these pieces of rock here, these are technically sediment. It doesn't matter how big it is. It could be the tiny grain of sand or a huge boulder. It's considered sediment if it's not part of a large consolidated mass of rock. These large consolidated mass of rocks, those are called bedrock. And the crust is composed of these large, widely extended regions of consolidated rock, known as bedrock. The crust is not composed of a bunch of tiny rocks that can fit in your hand. So these large units of rock. These hand samples are just pieces of bedrock that have been removed, either by people or by natural processes, and they're technically considered sediment. So this is bedrock right here, and pieces of the bedrock break off and become sediment, and that's all sediment down there. And we'll talk when we talk about why it's called bedrock, how it gets that name later. So if you see rock that's made out of layers of shale and limestone, what was that area like in the past? Well, to answer this question, think to yourself, where is both mud, which is the type of sediment that lithifies to form shale, and the remains of calcareous organisms like clams, or oysters, or coral. There's also little tiny organisms, little tiny plankton in the ocean that make exoskeletons out of calcium carbonate. But where is both mud and the calcareous remains of organisms that lithify to form limestone both deposited? Do we find mud and shells in the ocean, desert, mountains, or river valley? Well, if you chose A, that is correct, because A, we have mud that's deposited on the sea floor, so that mud will lithify to form shale. We also have different locations. We can have the remains of organisms made up of calcium carbonate being deposited that'll be lithified to form limestone. So if we find shale and limestone together, it tells us it was likely an ocean in the past. So if you wanted to learn what life in the surface environment was like in Rhode Island 300 million years ago, what type of rock would you look at? Would you look at igneous rock, metamorphic rock, or sedimentary rock? Well, if you found igneous rock, that would tell you, well, at least there was volcanism, or there was molten rock coming to the surface, or there was molten rock deep beneath the surface. Tell you one of those two things. Wouldn't necessarily tell you anything about life, right? Metamorphic rock, if you find more metamorphic rock from 300 million years ago, that'll tell you that rock was exposed to a large amount of heat and pressure. So there's likely a tectonic plate boundary around, but it's not going to tell you much about life or the surface environment. Sedimentary rocks, on the other hand, they'll tell you what type of sediment was being deposited. The type of sediment that's deposited is characteristic to the environment, right? When you think of a beach, you think sand, right? So if you have sandstone, that could have been a beach. You think of slow moving water, like in a slow river or a lake, you think mud, right? So muddy bottom, that mud lithifies to form shale. So if we find shale, think of slow moving water. Could be a big river or a lake. And so also in those sediments can be buried organisms, and remains of organisms can be preserved as fossils in those sediments. The sedimentary rock tells us the most about what the surface environment was like and what life was like in the past. And that's why in historical geology, we pay really close attention to sedimentary rocks. A lot more attention to sedimentary rocks than the other two types, because they tell us the most about what was going on, what sort of environment was present in the past, and what was living on Earth in the past. But like I said, that doesn't mean igneous rock and metamorphic rock can't tell us anything. So what do these igneous rocks tell us? So we can see these layers of basalt. Okay, so these horizontal layers of basalt. Well, basalt is an igneous rock, which forms from molten rock solidifying. And so it looks like there was layer after layer after molten rock. Well, what sort of environment would layer after layer of molten rock be existed? Well, you could think of maybe it's a volcano, right? This is the crater of the Greek island of Thera, which is a volcanic island. And each of these layers of basalt is the result of a volcanic eruption in which the lava flowed and solidified. And so you have a lava flow, and then later on a lava flow on top of it, later on a lava flow on top of it. So each of these layers is a lava flow, and they just accumulate on top of each other. So these layers of basalt tells us that this is a volcano in the past, and it had multiple eruptions in which this basalt was deposited. Other clues about the past we could find in, say, for example, sedimentary rocks are ripples. Right? So you can see these ripples in this sandstone. Well, we know if water is moving over sand, it can cause ripples or form ripples in the sand. And so those ripples can be preserved if a new layer of sand is deposited on top of them. If that sand is lithified, those ripples will be preserved. And they'll be preserved in the rock that the sandstone forms. And so this environment was likely some sort of beach, right? Either the beach of an ocean, a lake, or a river. Some sort of beach where water was flowing, shallow water was flowing over sand. Now, the three types of rock on Earth, they're always cycling or being transformed into other types of rock. So what's a sedimentary rock today wasn't necessarily always a sedimentary rock in the past. It won't always be a sedimentary rock in the future. Same is true for igneous and metamorphic. They get transformed into different types of rock through what's called the rock cycle. And so the rock cycle, this is just an illustration that kind of models it. It illustrates the interaction between the internal and external processes on Earth which drive the rock cycle, and how the three different types of rocks can be transformed into each other. So for example, if we start with sediment, right? sediment is deposited, it's lithified, and turned into sedimentary rock. Now, if that sedimentary rock is exposed to heat and pressure, it'll be metamorphosed into a metamorphic rock. However, if that sedimentary rock is exposed to a large amount of heat, it can melt and become magma, where it cools to become igneous rock. So sedimentary rock can be either turned into metamorphic or igneous rock. Conversely, if we have igneous rock, that igneous rock can be exposed to heat and pressure and turned into a metamorphic rock. Or that igneous rock could be exposed to the elements, like the rain, wind, glaciation, other things that break rock down. We'll talk about what weathering is in our next lecture. That igneous rock can be weathered or broken down into sediment. That sediment is then transported and deposited, and then that sediment is lithified and turned back into sedimentary rock. And finally, metamorphic rock, it can be heated to the point where it melts, then it solidifies, and it forms igneous rock, where that metamorphic rock can be exposed to the surface, where it's weathered, broken down into sediment, which is then transported, deposited, and lithified and turned into sedimentary rock. So all three types of rock can be transformed into the other two. And we call this the rock cycle. And this is always happening. As we speak, rock is being destroyed, or I shouldn't say transformed. I should say transformed. As we speak, rock is being transformed from one type to another. And so new rock is almost constantly forming on Earth. And so how the rock cycle and plate tectonics is related is that plate tectonics is the driving mechanism of the rock cycle. So these plates, whenever they interact and where they interact and how they interact, determines to some extent what type of rock forms. So for example, if there happens to be volcanism at that plate boundary, we're going to have igneous rocks form. If rocks are being squeezed, if there's heat and pressure along that plate boundary, metamorphic rocks are going to be formed. If rock is pushed up in the air to high elevation where it's weathered and broken down into sediment, that sediment is transported and deposited, then sedimentary rocks are going to form. Sedimentary rocks often form where not a lot's happening, and sediment can accumulate and later be turned into sedimentary rock. But plate tectonics is what drives the rock cycle. If plate tectonics was not operating on Earth, the rock cycle would shut down. Rocks would stop being transformed from one type to another. So for example, on Mars being a third of the size of Earth, it has cooled to the point where it no longer has plate tectonics. And so the rock cycle shut down. And so what's an igneous rock on Mars will remain an igneous rock on Mars. What's a sedimentary rock on Mars will remain a sedimentary rock on Mars. They're not transforming from one type to another because there are no plate tectonics on Mars. So by knowing a rock, how it forms, and how and why it forms, we can learn about the geologic history of an area. So this unit of bedrock here, this is the Cockeysville marble. It's in Maryland. And interesting fact, it's marble that was quarried from this bedrock that the Washington Monument was constructed. Well, this tells us about the past. So marble is a metamorphic rock, a non-foliated metamorphic rock. So it's a non-foliated metamorphic rock. So it's formed because it's non-foliated by rock being exposed to heat. So it's being heated. Well, what type of rock is transformed into marble? Well, limestone. Limestone is metamorphosed by heat into marble. So we know that, well, because there's marble here, that this area, this rock was exposed to large amounts of heat. And the rock that was exposed to the heat was limestone. Now, because it's limestone, we know limestone is a biochemical sedimentary rock. Biochemical sedimentary rock. And it formed from the lithification of the remains of the calcareous remains of organisms. So calcareous, that means calcium carbonate, calcareous exoskeletons and shells were lithified into limestone. So what sort of environment is calcareous exoskeletons and shells deposited? This is probably an ocean. So this is an ocean in which calcareous exoskeletons and shells were deposited. They were lithified into limestone. And then that limestone is exposed to large amounts of heat and is metamorphosed into marble. So by knowing how this rock marble forms, we can put together kind of some idea of what happened in this area, right? And that it once was an ocean. You know, in order for this material, this calcium carbonate that the marble is composed of to be deposited, it was like an ocean for where the remains of organisms, their secretions, their shells and exoskeletons were deposited. And so that's just one example. And we'll look at this more in depth, you know, using the rock cycle to kind of piece together the history of an area based on type of rock. This is just a little introduction to it. But an example of how understanding of how and why and where rocks form, in a sense of what happened in the geologic past. That's it for our lecture on rocks.